So we'll be discussing these key elements today. Where is the data? How do I access the data for local use? The gateway and how to get data into the cloud. And also, once it's there, how can I visualize it and what can I do with it? And then we'll have a Q&A at the end. So if you put any questions in the chat or the Q&A section throughout the webinar, we'll have a look at those on the end. 1 second. Okay, let's get going. So where is the data? At the moment, it's nowhere. It doesn't exist. It's in the sensors. It's not been created yet. We need to get inside those sensors and start generating the data. Now, they would normally be creating data all the time in their usual production environment. So ons and offs, distance values, all that sort of thing. But we also get additional data out of these new IO-Link based sensors, such as power uptime, quality of run, quality of teach, and lots more besides that. We know that this is a very interesting time in the world of automation and digitalization, and we know it's a daunting prospect to get all your data out of the sensors and start trying to make some real use of it. Perhaps you've already got on the road, or perhaps you're waiting for the right time to start. Whatever stage you're at, we reckon we can help you. We've got solutions in place. And this today is just me taking you through a basic setup of how to get some fairly straightforward data out of the sensors and into a cloud-based platform. So inside the demo case I'm going to be using to go through this, we've got a SIG200, which is our IO-Link master. We've got a SIG100 on the right-hand side. We've got something called the TDC, which is our telematic data collector. That's the large blue box. We've got an IMC30, which is an inductive sensor, one of our IO-Link enabled inductive sensors. FTS, which is a flow and temperature sensor, which is the device on the image with a long probe. WLA16, which is a retroreflective sensor. And a couple of digital I/O devices that we're going to be using. There's a little optical sensor and a lamp plugged into the SIG100. Let's see if I can show you that. So there's the little optical sensor, and below that is the lamp. So we're going to quickly talk about the SIG200 and the TDC, and hopefully we'll end up somewhere similar to the image you can see on the screen there, which is data being transferred from some of the devices and popped into the cloud on a dashboard environment. Right, SIG200. What is it? Well, it's a sensor integration gateway. It allows us to connect any IO-Link device and also standard I/O devices into the system in a simple, cost-effective way. Okay, and you've got to figure out why are we doing this? What are we going to do that's going to benefit you? So you can get access to the sensor data, no matter where those sensors are in the machine. For example, if you've got quite a large machine and the sensors are mounted in a place where you can't even see them, let alone get to them, you might need to have the ability to set these things up remotely, which we'll go through in a little bit using the web server on the SIG200. So we've got full transparency from the PLC all the way down to the sensor. It's not an expensive thing to get started with. There's no reason why you couldn't start with one IO-Link device and move on from there. Although clearly the more information you're able to glean from your system, the more useful it will become. We mentioned the web server. We'll go through that in a little bit. And there's also some onboard logic on board the SIG200, which we can use for some edge-based computing, which decreases the load on the PLC a little bit, and also potentially can decrease the network traffic load as well. This SIG200 has a REST API on board, which means we can communicate over an HTTP protocol, and we can get access to the IO-Link data over that platform, which is quite a useful way to get access to this information. TDC, we use a lot of three-letter abbreviations at SICK. So the Telematic data collector allows us to connect and get access to all kinds of devices and access the data from those different types of devices. And then we can get the data out via a few different options, MQTT, OPC UA. We can go over a local network, Wi-Fi, or we can even use SIM cards, which you will see in some short video footage that I'm going to show you in a little bit. The data is being transmitted over SIM card in all of the examples you'll see today. So what are the real benefits of this to you? Sensor status login in the choice of cloud that you choose. So whether that's AWS, whether it's Azure, whether it's something that SICK provides, because we've got lots of new solutions coming online all the time. It forms the foundation actually for active and predictive maintenance, because once you can access this hidden data that's only recently really become available, then you can start using that data to make predictions and quite accurately maintain your system, as opposed to just following blind maintenance patterns. We've also got here user-defined real-time alerts. That's a complicated way of saying we can send text messages and emails at the moment of failure or the moment of perceived failure. Simple configuration. There's no software or license costs from SICK. Once you've purchased the TDC itself, there's some onboard setup software, but we don't charge additional fees for that. And also, what's quite a useful feature is that there's onboard GPS systems. So if you've got mobile systems, you can also extract the mobile positional data from the TDC. So the gateway itself becomes a source of data. So IO-Link gives us an insight into the workings of a sensor, but we need a way to understand what's going on. And you may have heard talk of IOD files, which every IO-Link sensor has its own IOD file. So it's an input-output device description file. And within there, we get all the information about process data, but we also get the information about this hidden data, the service data it's sometimes called, or parameter data. And that's accessed acyclically alongside the process data. So the process data is cyclical and comes through continuously, whereas the parameter data or the service data comes through on request, so it's acyclic. We can sort of get a bit of a grip on what's happening and what this data is by looking at the indexes. And what we need to do is convert this, what ends up being quite a long data looking file. We need to be able to see that in a way that we can understand. Okay, so for example, we've got a line extract from the IOD file at the top, and we're looking at index 180. Okay, great, index 180. Well, within our documentation, we reference that 180. So we know that the number within the IOD file is referenced within the documentation. And then we also get to see the variable name that is attached to that index number. So this is data index for the current receiver level, the live current receiver level. So if I send a signal to the sensor and say, I want to read index 180, or I want to read the variable name be current receiver level live, I will get the current information for that index, but it'll only be valid for that cycle. Once we've got an IOD file, what it does mean is that we can convert all of this, what could be perceived as complex information, into a format that we can easily understand. So something that's written in English or whichever language you speak, and also some graphics that can go with it that are associated with the device itself. Now, we've got to start getting this data out of the sensor. So how do I access the data for local use? Let's have a look at the demo case and sort of figure out what we're trying to do with it. So we've put the demo case together, and it's effectively pretending to be a very simple chain drive system, which could be found in a flow wrapper, for example, something like that, where we've got a drive, we've got some cooling system on the drive, We've got a chain that we're monitoring with the inductive sensor for drift. And then we've also got basic optical detection to check for products. We're going to go through a video in a moment. And this is video that I've recorded as live, but I thought rather than risk any technical failures on the day, I will talk over the video, but it was recorded live. So hopefully you'll be able to see what's going on there. Just as a quick point, the stuff on the SIG 100, the basic optical sensor, we use it on the demo case for inhibiting the output lamp. If, for example, you were doing maintenance on the chain or the chain drive and you wanted to stop the lamp from flickering on and off randomly, you would usually have maybe an override key switch or some sort of override code. We've just represented that with the simple optical switch. And therefore, we can inhibit that sensor. So just a demonstration of the basic I/O, the very basic level of data there. One of the key abilities of the SIGs as well that I did touch on before was the fact it's got onboard logic. And that basically allows us to replicate some reasonably complicated systems. Nothing to the level of a PLC, but we're not trying to say that it is a PLC, the SIG 200. It's a logic controller more than anything else. Right, so we're going to be referring to contamination or dirt or signal quality, receiver level, those kind of terms. And what we're going to do to show that, if you just have a quick look here on this video, there's a little window, a little plastic window there. That plastic window is representing contamination. And you'll see that when I pop it in front of the optical sensor, we will get a drop here. We'll see the signal drop. Okay, so this background image was taken from the cloud information, and the signal is almost instantaneous. We're not saying it's real time at any point here, but it is fairly quick, the update usually. Okay, so this is the web server from the SIG 200. We briefly touched on that. If we log on to the SIG 200 via the web server, we get to see an overview, like you saw there, with quite a useful amount of information. And then we can go in and see things like the settings. And more importantly, when we're setting the system up, we can access the IO link ports, such as you see here. You can see on the right-hand side, we've got IOD files that are already associated with certain ports. We can see we've got digital labels, so we can name the ports, and makes it a lot easier to see what's going on when you first log on. You can tell which devices are connected to where. And then if we drill down into the actual ports themselves, so here's port number 1, that's an inductive sensor. You can see there's 4 switched inputs, so 4 different digital switches and an analog value, which is very important. The grey boxes here, the process data is represented. These are digital switched outputs from this sensor. So this doesn't have quite as much process data associated with it. But I'll take you through in a second that there's a bit more to this sensor than meets the eye. So at first glance, it's just ons and offs. But when you dig down a little bit further, you start to see that there's more to it than that. Okay, so on the right-hand side, we've got access to our parameter data, as you can see here. And what we're going to be looking at in particular, I'll just show you. I've got the pointer here next to the quality of run. So that's the value we're going to be interested in looking at. And what we're going to do, I'm going to be inserting contamination effectively into this system. And we'll be able to see that as that's put in and taken out, that value will change. Now, because it's acyclic, the way this web server works, we have to click read data every time we want to read the information. Otherwise, it would be cyclical data. So you can see there the quality of run had dropped to 67. That's because I put the contamination window in place. And it's dropped again there to 51. Now, there is an algorithm running on that sensor that works out, relative to its initial teaching, what is the quality of the signal coming back to that sensor from the reflector. And over time, the algorithm works out again and again and again what that quality is. Now the window has now been removed, and you can see I'm continuously reading that value out, and it's gradually returning back up towards 100. 100% would be a perfect situation, as if it had been taught in. Anything less than 100 indicates that either you've got dirt buildup on the window, or you've possibly had a knock and either the sensor or the reflector has been misaligned. It's absolutely possible. But it's all very useful stuff. So we talked about the logic editor. Now we've clicked into the logic editor here, and you can see quite a lot of blocks going on. It's a drag and drop environment, as you can see. Just drag them down from the top, pop them into the logic editor. So now what we're doing, we've got access to the data. We've seen that in the web server. We can see the process data and we can see the service data. And this logical editor here allows us to manipulate the process data and do various operations on it. So what we've got the analog value coming in from the inductive sensor, and there's 3 compare blocks there. And basically we are seeing what the value is, and depending where it falls within those compare blocks, we will give an output. And in this case, we're saying that it's either between value A and value B, and that we would say is an acceptable level. And if it's below another value, we would say that that was an unacceptable level, implying that perhaps the chain had drifted out of position and was no longer giving a value that satisfies the conditions that we've laid out. So data flows from left to right, and we pass that information over to these blocks on the right, and you can see with S2 IL1 is highlighted there. So that's connected to port S2, and it's input logic 1 is what that's referring to. That is actually connected to the device called the SIG100, which is connected to port S2. And what we'll see in a second, I'm going to bring up the SIG100 logic, and we'll be able to see that S2 IL1 is an output on the SIG200, but when we go to the SIG100, you'll see that it then becomes an input on the SIG100. Okay, so here's a highlight of the SIG100, and there we can see IL1 on the left-hand side. Now, it's not referred to as S2 IL1 because the SIG100 hasn't got any ports of that nature. It can only have digital I/O. So as far as the SIG100 is concerned, it's just IL1. If you had multiple SIG100s connected to your SIG200, then you would have S2 IL1, S3 IL1, S4 IL1, etc. Okay, I hope that makes sense. It looks quite complicated, but actually it's not as complicated as it looks. It's drag and drop. It's fairly straightforward. I just thought it would be useful to see localized use of the data without needing to go through complicated PLCs in this particular instance. So we've got edge-based control. So there's various features on the case designed to show the data locally. So we'll start local and we'll make our way up to cloud-based data. So within the case, there's various components we've talked about. We've got the IMC is in the top right on this shot, and you'll be able to see in a second that we're going to demonstrate a chain drift situation. So I've got a metal target, and I'm going to offer that up to the IMC and put it in what position that would be deemed to be normal. So the chain is in an acceptable position, and we get a green output light. Now, if the chain were to drift, such as shown here by changing the position of the metal in the field, in the detection field, then we would get a red output light. And immediately we've got a localized solution for chain monitoring. Now, we're using a lamp to show this. Those digital outputs could quite easily go to any system you like. And we're just varying that around, and you can see we're getting useful information. But then if I cover the optical sensor, the inhibit sensor, doesn't matter what I do with the metal target, it's being inhibited, as you can see there. So we've got an input being used via the SIG100 that's going through to the SIG200 via the logic and creating a useful system. I'm now triggering the optical sensor, and the way we're demonstrating that that's being triggered rather than the inductive is both lamps come on simultaneously. So that just shows that we've got useful features. We could have maintenance overrides and things like that easily via a key switch or something of that nature. So yeah, using the onboard logic, it's really possible to control lots of local I/O without the need to even go to the PLC at this juncture. Okay, so we've seen visual feedback from the actual device themselves in terms of the lamp. Now we can see that information in a slightly cooler way. So this is a local dashboard. We've got an FTS flow reading there. So you can see the device with the long probe sticking out of it. That is a flow meter, and that is in a simulation mode, which is being driven by the TDC. So that's being told to be in simulation mode. I'll just pause that for a second. The simulation mode on the FTS is actually very useful. If you've got a wet system, something that would normally be fluid filled, and your wet side of the system is not yet ready to go, there's nothing to stop you popping the FTS into one of its simulation modes and getting the data out. As you can see here, we're getting data out. It means you can test all your dry side. You can carry on doing the wet side build in the process. So that's pretty useful. I've just grabbed the probe there, and you can see the temperature at the right-hand side of the window is creeping up on that graph. So straight away, if you were to click onto this dashboard, you've got very useful logic and data coming back and being visualized. So the two graphs of process data and the two green ring dials, they are actually being derived from parameter data. Okay, so what I'm showing you here, I've covered the reflector from the W16, and you can see the receiver level's gone to 0, which is what we'd expect because you've covered the reflector. There is no light coming back. Now, if we get our trusty contamination window and we pop that in front of the sensor, you'll see in a second, because this is on a few seconds, the update frequency on this dashboard. It's not instantaneous, but we can see the live receiver levels drop down. But also now, because what we've done, we haven't covered the sensor, we've just dirtied the sensor. So now the quality of run has also dropped. So it's a very smart system. It knows when you're detecting a product. That's not a quality of run issue. It's supposed to turn off when you detect a product. But when you contaminate the sensor, then we start to see quality of run being given out. And that leads us on to what you would want to do about it. So on the same localized dashboard, we've got the ability to enter into one of two contact number areas, a phone number, either for the FTS alert, so that could be that would be a flow rate if you've got a pumping station or something like that, and you needed to trigger an alarm if the flow rate dropped below a certain value, or conversely went above a certain value, you could do that. But for the purpose of this this demo, we're going to look at the W16, which is the optical sensor. So we'll pop some contamination in front of the trusty plastic window, and we'll wait for the quality of run to drop there. Here we go. And then in a few cycles time, we will trigger the request to send a text message alert. And I'll get my little mobile phone ready. And what we're going to do now, we're just waiting for this text message to be triggered and to be sent. And the TDC is what's currently responsible for sending this this warning. You'll see that come through in a second. And the good thing is you can set up a different text message for each alert, and there really is no limit to the number of different alerts you can have, because the TDC is quite a powerful piece of equipment. So the warnings come through, reads, warning, your quality of run on the W16 device connected to port 4 of the SIG200 is outside its expected limits. So that's the warning for that particular alert. So we'll remove the window, because I didn't want to be getting texts for the next few days. And we can quickly say, right, remove the phone number. There we go. And the alerts have now been removed there. And what we'll do now is move on to an OEE dashboard. So overall equipment effectiveness. Now we're really starting to make some use out of all of this data here now, and we're still not in the cloud at this point, but we're making our way there. So we've got various bits of information now, and we are approximating how OEE might be used in a real workplace. So I'll pop the little piece of plastic onto the background suppress sensor there. And what we've done with this case, if that sensor's covered for 10 seconds or more, case jumps into demo mode. And what that means is that the lamp starts flicking from green to red. And every time I get a green lamp, I get a product detection effectively. I get an incremented piece of count. And also I can trigger rejects via the optical sensor. So you can see I just ran my finger in front of that, and that went up from 10 to 11 on the reject pieces. Now with OEE, we've got the opportunity to look at things like quality of the products. So how many rejects we got out of the products produced. We've got availability, which is basically a measure of how long the machine was available for during the shift or during the time frame that we were interested in. And also performance, which is how well the production ran whilst the machine was available. And if you multiply all three of those together, you get the overall equipment effectiveness, which you can see in the top left-hand corner there. Now, for the purpose of the demo, we've put a couple of sliders on, so I can directly affect the ideal run rate in terms of parts per minute, and I can directly affect the expected amount of downtime for the shift. So these values are given with the expectation that the shift will be completed, but if the operator walked away right at this moment, this would be the values that you would get at the end of the shift. So we'll make a change there. We'll drop the ideal run rate. This is quite useful to see. Straight away, the performance of the system jumps up. However, the availability is also reflected in this. In a minute, you'll see, because we've also incurred downtime. So the machine was available for less time, but in the time it was available, we produced quite well. And obviously, the more changes you make, the more ways there are to show that data within this dashboard. It's quite useful. I think there's quite a lot of people making use of this kind of information now. There are systems that you can get hold of that purely concentrate on this, but I say why restrict yourself to an OEE system when you can use the TDC to do that and so much more. So it's okay. We've got localized dashboards. That's all well and good. But then, what if we want to review that data remotely? What if we want to share that with somebody who isn't in the factory? Well, why not replicate that dashboard in the cloud? So in the background, you can see we've got a cloud-based version of the localized dashboard, and the TDC is uploading the data that we've produced locally, and it's sending it up to the cloud to the dashboard in the sky, as it were. You can see that the dials are indicative of the values shown on the localized dashboard. So we'll make a little change there, and you can see that those values are reflected locally and also in the cloud. We'll make another change, incur a lot of downtime. You can see our availability just went through the floor. Our overall OEE is pretty bad, although performance is great because in the time we had available, we did a pretty good job. But unfortunately, OEE is more than just one measure. Now, the great thing about having it in the cloud, you can see here, we've got a record of what happened and when it happened. So we could go back historically and look at various days, how the OEE was managed, what the availability was like, what was our quality like, what was the reason that my OEE itself was not higher. And you'll probably find it's a combination of all three of those things. But sometimes it's more one than the other. For example, if you have a lot of downtime, then you've got to fix that. If you have a lot of rejects, that's not likely to be because of the downtime. It's more likely to be because of the systems you've got in place to produce high quality goods. So the great thing about having cloud-based data is that we've got access to that data historically. So it's not just a live readout, and that's really useful. Okay, so how did I get that data up there? We had a look at a dashboard example in the cloud. How did we get it there? Because that's what we're really interested in. How are we getting the data to the cloud? Well, that's as you see there. That's where the TDC really comes into its own. So on board the TDC, we have a few containers, but the one we're going to focus on today is a NodeRed container. So NodeRed's a very useful programming tool, and it allows us to communicate in whichever form we want, really. But we're going to use the REST API on the SIG200, and then using a JSON formatted code, we're going to program the information that we've obtained. We're going to condition it slightly, and then we're going to send it to the cloud. And in this example, we're going to do it with the MQTT protocol, although there is also availability for OPC-UA connections. So this is an example of a NodeRed flow. And in a minute, we're gonna go through the process. But hopefully you can see the kind of thing we're dealing with. So for example, in the preparation node, we might have information such as this. So we're saying, how is the header being sent? What's the payload construction? Then we're going to tell it how we're doing it. So that information there is basically configuring the REST API communication. And then once we get the information from the SIG200 or the devices, we condition it. So we take the information in, we format it to a version that we want, and then you can see, let me show you in here, this message topic. That is the IMEI number of the TDC, so that the cloud that you're sending it to knows where it's come from. And then it's the name of the variable that we've specified up here. Okay. And then that information would be found in that node, and then it gets passed. It gets passed to an output node, which is the green node. Now we have the option of connecting it to other things, such as the MQTT node, and you'll see that in a couple of moments. Okay, we talked about the REST API, and I want to make sure you get to see a little bit of what that would be like. So here we've got a piece of software called Insomnia, which is a REST client. And we are basically pretending to be the TDC here. So what I'm doing is clicking send, and I'm sending the information in the middle window across to the SIG200 via the HTTP command at the top. So I'm saying I want to read the device, and I want to know what the current receiver level live is. On the right-hand side, we get a response from the SIG200 saying, yeah, I'm okay, and the receiver level live is 98 in this particular case at the moment. I'll make sure that you can see what I'm talking about. There's 98 next to the laser pointer. And what I'm doing now, I've put the trusty contamination window in, and I want to see what happens if I keep reading that. So we keep sending the command, and we're going to read it, and we can see it's 72, 73. So our receiver level live has plateaued around about 72, 73. But what about quality of run? That's not the same thing. The quality of run dropped significantly because the sensor is dirty. So we've got either dirt on the reflector, on the window of the sensor, or something's been misaligned. And straight away, I think you can see the value of knowing that information. If you've got a system that can understand what quality of run actually means, then it can create its own alerts and generate its own maintenance requests, because it's no longer dependent on people going around with cloths once a month. It's become smart. That data can be manipulated and utilized to give you an autonomous maintenance procedure in some respects. Okay, so here's the NodeRed we touched on a little bit before. This is pretty cool, and up until the TDC was dropped in my lap, I'd never really had a chance to play with this. But having had a bit of a chance to get involved, it's really useful. A lot of this can be done once you've got a basic understanding of what's happening. You can cut and paste various command types and just make small alterations. So we're going to go through a couple of the windows here. Now, if you look, get the laser pointer up. If you look here at this receiver level, that receiver level next to the pointer, that was what we were looking at in the REST API window. So it was around about 72, 73. In this situation now, it's sitting at 76. But you can see the quality of run below it, we're getting a local bit of information out. That was dropping. Well, I've just removed the bit of plastic contamination, and we can see the quality of run is going back up. Not as quickly as the receiver level, because that's shot up back to 98. But the quality of run is tracking back up. So the good thing here is that even if the system does request autonomous cleaning, it also knows that it's been done because it's getting the feedback from the sensor, which is pretty cool. So here's just a quick example of how the MQTT node would work. So we need an IP address, and we need some secure logins for the cloud that we use, our development cloud. We'll touch on the AWS side of things in a little bit, Amazon Web Services, because this demo is also passing data, the same data more or less, with slightly different format. It's also passing data to the AWS cloud, and you can see that here. So in this window, we've got some data being sent to both the SIC cloud, our development cloud, and the AWS cloud. And this is the information highlighted that's going to AWS. So you can see the server address is a little bit different to the one that we used on the other MQTT. So there's one more thing to say, and that is that with the MQTT, not only do we have the ability to send information to a cloud, but if the MQTT broker is set up properly, we can receive data from the cloud, and that's what this screen is showing. I know it's not very exciting, but that purple node there, if it gets some information from the cloud, that activates, and you then can use that information, the fact that it's sent an output, to control whatever you want to control. You could control remote teachings, you could control changes to specifications and what have you. Clearly, you would want to make sure that access to the other end was locked down. But equally, it's a very powerful feature. So we can do local edge computing in the TDC, but what we can also do is we can enable more powerful computing if we move that data somewhere else. So we've got the data. We've shown that we're using the REST API, we're using the NodeRed on the TDC, and basically we are sticking that data into a cloud of our choice. So as you see here, the commands such as MQTT are not cloud specific. It's configurable, and we can send data to wherever we want. We've shown examples of the SIC development cloud, and we've shown examples of the TDC sending information to the AWS area as well. As I say, Azure, any other cloud provider would be used. So in AWS, I'll show you really quickly in a minute how we can view some of that information. And you can see in the next short bit of footage our development cloud and also the AWS cloud. So this is our this is our development cloud. So this is a way of us showing the kind of things that can be achieved. So we'll pop the demo case into demo mode by covering the BGS sensor, the little optical trigger. And as I said, this information is being passed over to the cloud via the SIM card that's installed in the TDC. However, there's nothing to stop you connecting the TDC directly to the Wi-Fi where you've got it based, or even the LAN, and going through the relevant firewalls to pass the data up to the cloud. So let's have a look at what happens when we start playing with some of the sensors. So now we're in demo mode. You can see that IMC count here, it's starting to go up. But you can see that I've also just grasped the probe of the FTS, and you can see here that the temperature, FTS temp, that started to increase as well. So straight away, we're not talking a few minutes behind in the lag. It's not far behind. It's almost instantaneous. But it doesn't need to be, because the whole purpose of the cloud-based data is not really to have live reaction immediately like you would do in a real-time system in the factory. It's about storing this data and creating value from it. So we've got the temperature. You've seen how that reacts. You can see below that the flow, and that is the simulation mode. Clearly, this would be a wet sensor normally, but because of that amazing simulation mode that we've got on there, we can view data even though there is no fluid to be measured. So you can see the IMC count is incrementing, and that's counting in batches of 100. Again, just to sort of simulate a real world example of some sort. We're counting 100 counts and then automatically resetting the count back to 0, get up to 100 and then drop to 0. You can see when I've put a metal target now, we're representing the chain. We can give live error readouts or live condition readouts. So we're saying, well, that was a proximity warning. We're saying there's no metal at all there now. You can see the sensors detecting no metal at all. Therefore, in this demo, the chain has snapped. And that's important. That's worth making note of. We would automatically assign a breakdown team to that for this particular system. We would flag downtime, and we would do all kinds of other useful reactions based on the data that's being generated. Now we're going to look at the system data. So this is the acyclic data, whereas the other screen was primarily process data. You can see we've got a lot of information on the left-hand side, which is the FTS data. The supply voltage is quite a nice one. That would be quite a good way of monitoring what's going on in terms of the voltages on the system, and that's measured from the FTS itself. So this is the information from inside the sensors. This is the extra data. So here you can see I've just covered up the optical sensor, and the receiver level has responded on the graph there by dropping down to 0 because no light's getting back to the sensor. And you notice the quality of run doesn't drop at the same time because the system or the sensor is smart enough to know not to generate quality of run issues on detections. It only generates quality of run issues when there's something to report, as in when the sensor is dirty or misaligned. So we'll take our plastic window again, we'll pop it in front of the reflector, and what we'll see here is that the receiver level drops to around about 70, 72. We saw the 72, 73 sort of value, depending on the angle of the contamination. And then you can see the quality of run is dropping significantly now. Now that will plateau in a second, but because the algorithm is time-based, it takes a few seconds just to get to its final point. But at this point already, I would be setting an alarm somewhere in the system. The system would either be triggering an SMS, an email, or it would be sending a digital output to the system to say, hey, we've got a problem here. You need to sort it out before we have a failure. Now, the good thing is while that quality of run alarm is in effect, we can still produce, we can still work. The sensor will still work in its normal fashion. We've cleared the contamination now, and you can see the receiver level shot back up, and the quality of run is tracking that now and is back up towards 100%. So we're no longer struggling there. This is an example of how data might be utilized to compare systems now. So what we've got is two different demo cases, or two different systems, whichever way you want to view it. And we're looking at the throughput of those two systems side by side. So straight away you can see that the bottom graph is reproducing those batches more quickly than the top graph. And you can see as well, if we have a sudden increase in throughput, so I'm still in demo mode, but I'm also adding detections on the IMC directly. You can see that that's reflected on the bottom graph. We've just had a little surge, or a little blip, and you can see we can directly affect that. But the real beauty of this is that if you've got a factory, and this is a very basic way of showing it, but I'm sure you can understand it. If we had 9 or 10 of these graphs next to each other, at a glance you can see how things are performing immediately, which is very useful information. Okay, so we talked about the AWS cloud. We'll show you that here. So the case is in demo mode, as you can see, and I've just logged on to the AWS cloud. And on the left-hand side in the background, you can see the data that's coming through from the case to AWS. So the topic that I am subscribed to in AWS is IMC count. That's the name of the topic. And the information that's associated with that topic is at the bottom here, all of this information. Now, I've just put the contamination window, the trusty contamination window, in front of the sensor. And you can see, I'll just highlight that here. You can see quality of run next to the pointer is dropping off. So this shows that this is real, genuine data, and it's reactive within seconds. So I'm repeatedly uploading this information to the AWS cloud, and you'll see there we remove the contamination, and then the value starts to track back up. I think it's on a 3-second repeat, this one. So every 3 seconds it uploads the data that's currently available from the system. And there you go, it's tracking back up. There we go, working its way back up. Now, it's all well and good getting the data up there, but what use is that? Why are we doing it? Because I think that's really what's important here. So what we're looking at here is a graph of the production value, shift production value by FTS temperature. Okay. Now, although that doesn't seem to make much sense in and of itself, what we've got to understand, just right there, what we're seeing here is that certain FTS temperatures, so for example 37.1 and 36.7, those FTS temperatures tended to yield a higher production value overall. So what that means is that there was more production at those temperatures. That presumably is to do with the temperature in my office. That's primarily the temperatures that you see in my office. But that could easily be air conditioning as well. Now we'll switch the mode here, and you can see we've got similar sort of observations. So what we're saying is that for that value, 30, 35.2, 35.1, I think with the lid of the case shut and in demo mode, that's going to be the temperature in the case. So that is why most of the production is done at that temperature. But that could quite easily be, like I say, an air-conditioned office. It could be a production line where, you know, after visualizing the data and checking it, you know that certain temperatures within your production facility yield higher outputs. Now that's presumably just down to the comfort of the employees. They feel comfortable, they feel like working. If they're really putting a shift in and they're sweating cobs or they're freezing cold, less likely to put in quite a good shift for you. And even if you take people out of the equation, let's say it's robotics, they've got a preferred working temperature, and you will find that this data over time builds up and starts to present quite an interesting picture. Okay, that is it. Hopefully, you've seen some useful information, taking data from the sensors, the localized facility, moving that to a dashboard environment locally, and then tracking the data up to a cloud of your choice, and being able to make use of that data in a reasonable, real-world fashion.